want to tell you about it. And this new thing about the, what is it called? We call it digital ignition.
National ignition.
National ignition. That's the amazing stuff to hear, right? How many of you want to hear him? Raise your hand. You want to take a picture of this or take it with you?
Definitely.
It is my honor to introduce you, Mr. He told me, by the way, I had a hard time to know his name. Okay, I was reading a James, so on. And here's what it is, if you want to learn. Don't pronounce the G rather. Don't pronounce the G. Pronounce it as it is. I asked him for the next time not to write it. Okay? Look, my honor to introduce this beautiful speaker tonight.
Thank you. Thank you, everyone. Thank you. John Gjemso. I know I have a problematic last name, but it's, well, if you say it in Spanish, it's actually not the J, it's the G. Depending which language, that's how you pronounce it. Thank you for having me here. I'll tell you a little bit about myself and what the talk's about. These are a couple of things that I like to identify myself as. I'm most proud of being Latino. I'm a Latino engineer, scientist working in nuclear. I'm a maker, hugely STEM advocate, and hugely a grad school advocate. So I'll touch base a little bit of that during the talk. Before I get going, I just want to check the Zoom, the audio, everything's working fine. The camera,
This is if
all
I
good?
can hear it. I want to get back here. I'm kind of deaf,
Okay.
so I want to make sure that if I hear it, everybody hears it.
Awesome. Okay. Thank you. All right. So everything's working fine. The entire presentation is going to have three things, and I'll keep it very simple. I'll tell you a little bit about me, about my story. Then I'll tell you the main topic, what I do for work. And lastly, a couple tips I have for you for starting your educational journey. So a little bit about me. Like I said, I'm Latino. I actually grew up in Mexico. I was there until I was about 17. That is me going here in Cancun. My family's still there. And right before college, I moved out to the West Coast to begin undergraduate, work a little bit, and then go to grad school. My educational journey was not easy, and it probably resembles a lot of the challenges that you're seeing in these early years. My credentials involved my undergraduate degree at Cal State Northridge. I did mechanical engineering there. It took me a while to graduate. Like I said, it was really hard. Almost about 5.5 years to graduate. I didn't speak the language. I had no family members that were knowledgeable with how the universities, community colleges work at all. So there was a lot of learning on my own. I didn't know how to actually succeed in college. College was very different from high school, and it's even more different from high school in Mexico. So there was a lot of learning to be done in those years, on top of getting used to college and having to do homework and grades. So there was a little learning during that time. I had very limited financial resources, just like we all do when we're in college. And then I was also very unaware of college programs that actually provided support, provided some type of tools for you to move forward and to get over those challenges. Completely unaware of that. And then a lot of learning, and when I decided to go to grad school, it's completely opposite. It was fast, it was easy in terms of I knew how to what I was there was going to do. It was pretty efficient. I actually got a scholarship that paid for tuition, room and board. I actually gave me a stipend, so it was a complete change from what I experienced in undergrad, and that tends to be the case most of the time. So one of the main things I want to highlight is that from my undergrad years, I knew about programs that actually provided some tools, some help in case you get stuck, study sessions, study groups. So I went for nuclear engineering as my master's, and I'll tell you a little bit about why I decided to make the change. So I just walked you through what I did during my undergraduate years and then my graduate years. It looked something like this. I arrived about 18 years old. I had to find a campus job, and I had plenty of those. My college didn't offer summer classes. I heard that maybe there's some physics classes offered in the summer, which is great. But there was no classes taken in the summer, and I took that chance to take internships and find internships. I took 2 internships before I graduated at the Toyota headquarters, Kentucky, and at Medtronic. I graduated, and I briefly had a couple of jobs before I decided to go to grad school. I actually never wanted to go to grad school. After working for a little bit and doing engineering work in some of these companies, I said, you know what, grad school is the way to go. So I moved out to Oregon and I decided to start my program as a student researcher pursuing a nuclear engineering master's degree. Shortly after that, I joined my current job, the Lawrence Livermore National Laboratory. So let's talk about that, what I do for work. Has anyone heard about the Lawrence Livermore National Lab? Raise your hand if you've heard vaguely about, okay, it's like 3-4 people. It's actually a research laboratory that's funded by the Department of Energy. That just means we don't sell any products or any services. We get funds from the government to perform research in different areas. That's what it looks like. Back in the 60s, the government wanted to put together all the scientists and engineers somewhere here in the Bay Area to do the research in many fields. So they bought a 1 mile by 1 mile piece of land all the way outside, as far as they could get it from Livermore. And that's what it looks like that. It's been growing since, and there's, like I said, there's many research fields, many buildings, many laboratories within that space. The one I work at is not only the coolest, but it's the best one. Amazing what that does. But just in general, just to give you an idea, there's about 17 different national research laboratories across the US. Each one of them tends to focus on a particular field or a particular set of fields. And they're all across the US, as you can tell. They're really powerhouses for science to move forward. They don't sell any service, they don't provide any product, but they're really there to move science forward in terms of what we know as a humanity, right? Whether it's biology, chemistry, physics, it's really there to provide that expertise and advance the frontier of what we know about a particular subject. Okay, anybody seen this movie? Okay, so you're familiar, Oppenheimer. There was one national lab that actually started it all. Can anybody remember what it's called?
It's the one in New Mexico.
Yes. Remember the name?
I think it was in a movie.
It was a movie? Okay. It's called the Los Alamos National Lab. And if you've seen the movie, it's where they started again. They went out somewhere in New Mexico. That was the start and said, we want a piece of land here. And that's where they started building. So that's the national laboratory. And what they portray there is really how laboratories still work today. Right? Ooh, we lost some lights. Okay. So I'll tell you about nuclear energy and what I do. And just for, I'll give you a very small context of nuclear energy, nuclear power. Nuclear fission is splitting one heavy atom into two. This has been discovered back in the 40s, 50s. This is what gave birth to the nuclear weapons. It's often portrayed in every single power plant that you've seen ever. You know, Homer Simpson works in a power plant that uses fission. This is the picture when you think of a power plant. That is the way, the science and the technology that we utilize, nuclear fission. We've done it. Accident that happened. There's this sort of like bad rep associated with it. There's currently still many plants operating in the US and the world. Right? But that's not what we're working on. We're actually working in nuclear fusion. Very completely opposite. Instead of dividing the atom in two, we're actually taking two of the lightest atoms in the periodic table. Anyone know what that is? Lightest atom in the periodic table? Hydrogen. There we go. 2 atoms of hydrogen, and we try to combine their nuclei. When we do that, we actually get a lot more energy from joining them. They're no longer hydrogen, they become something else, and in the process they release a tremendous amount of energy. If we can find a way to harvest that energy, then we can use that energy to power our buildings or schools or hospitals, and just have a very different way of providing energy to our communities, right? At least that's a pipeline goal, that's a dream. So nuclear fusion is also the process in which the sun obtains its energy, right? We know this, we've studied it. That's actually what's happening at the very center of the sun. Atoms get split up and that's how the energy gets released. That's what we actually see here. So in a way, it's not quite solar energy like what we have right now with solar panels, but it's mimicking the sun here on Earth. And if we can find a way to have a tiny little sun operating here in the world or multiples on, it will be a huge amount of clean energy with no radiation waste, with no byproducts that we can really tap in as an energy source. Okay, so with this in mind, I work at the National Ignition Facility. Anybody's heard I know somebody's over there has heard of the National Research Facility. Anybody else has heard about it? Okay, cool. So this is one of the laboratories within the Lawrence Livermore Lab. That's the one I work with. And the facility has a name Ignition because the entire purpose of this is to be able to, once you fuse those atoms together, get more energy out than the energy that you put in. Okay, that's the entire goal. If you can get more energy out, we call that ignition. You've ignited the process, right? So they decided to call National Ignition Facility the whole purpose of understanding how to replicate this tiny star, the tiny sun, and being able to get more energy out than the energy that we put in. It was built about 15 years ago. That's a picture of what it looks like. It's actually very funny, but it's a group of scientists and engineers that were really good with lasers. The laboratory has a history of working in laser experiments. And they went to Congress and they pitched the idea. They told them, hey, we think that we can use our lasers, or maybe bigger lasers, to actually fuse those atoms together. And we're really good. We think we got what it takes to actually do it. Some other countries were still working on it, but nobody really had the inclination to pursue it. And they got the funding. They started building it. Now it's been, I want to say almost 20 years. For the longest, that's what it was. And that's what you see here is kind of like a small scale of what the entire facility now looks like. I'll give you a quick rundown of what the idea was. They said, we're going to create the biggest and most powerful lasers in the world. And we're going to shoot them all at the same time. Imagine if you start with 2 of them, right? You have one in each direction, and you put the atoms of hydrogen right in the middle. So you shoot both of them at the same time, and if you do it just right, both of them are going to start squeezing the atoms together, right? Eventually, if they're powerful enough, you'll get them to a point where they'll fuse, you'll get more energy out than what you put in. If you only use 2, you're running the risk of the atoms actually coming up from the top and bottom. So then maybe it's easier if you put another 2 on the top. But if you do that, eventually then it starts coming up from the sides, kind of like a balloon that you try to squeeze. So they settled down on 196 lasers, okay? Half of them coming from the top and half of them coming from the bottom. At the very center, there's a small target of hydrogen. This is not to scale, okay? The real thing, I'm going to show a picture, is smaller than a Tic Tac. So all of the lasers are shooting at the same time. They're the most powerful lasers in the world. This is the facility itself is the biggest laser facility in the world by both size and energy used. And all the lasers hit the tiny little pebble of hydrogen at the same time, creating the conditions necessary to fuse that atom and create fusion, more energy out than we come, or at least try to get more energy out than the energy that we put in from powering all these lasers. Great. I'm going to show here an animation in case my little scale example didn't work out. Hope it plays well. There we go. There's a very small delayed version of all the lasers converging. Like I said, it's 196 total. Half of them coming from the bottom, half of them coming from the top. All being shot at a tremendous amount of energy into this tiny little pebble of hydrogen in the middle, right? Just so you get a little bit of idea of what this scale looks like. Here are the pictures. That's how much hydrogen we're actually shooting. And that's actually just the outer layer. The actual hydrogen that we use, it's inside of it. So it's very, very small. And you can ask, well, how is it that it's so small and you're telling me it's the biggest laser facility in the world? Again, the fusion process creates tremendous amount of energy if you do it correctly. And that's what we're trying to understand. Right? There's a few pebble hydrogen isotopes of deuterium and tritium. There's a secret recipe or a secret sauce, if you want to call that, to what that mixture is, right? Obviously, you want to create this as symmetric as possible, and you want to contain it enough so that when it actually implodes, you get as much energy out as what you're putting into your lasers. So there's a little bit of a try and error that's been going on now for years. You also want to be very good at timing your lasers so that all of them hit the target at the same time. You don't want some of them hitting it first and then some of the other one, because then you start to get this asymmetric compression of the pebble. So you want to do it and time it just right. Again, why are they so small? Well, let me paint an example here. If you see these tiny little weights in the gym, about 8 pounds, if they were actually made out of this hydrogen pebble material that we use, that could power the city of San Francisco for about a year of continuous use. Don't have the technology, we're not there yet,
Yeah.
but that's how much energy there is inside of these pebbles, right? It takes very little to tap into that energy and be able to provide that energy. Now, that is with about as much inefficiency as you can think of from a regular power plant. So there really is a lot of energy to be tapped into if we can learn how to do it right. The entire facility, the entire idea that was pitched to Congress is called National Election Facility because the promise was that they can get more energy out than the energy they put in. People all around the world are trying to replicate this, different means. We're using lasers. Some people use a magnetic field. Some people have tried it with accelerators, different methods. But at the very end of the day, everyone's trying to get more energy out than we put in. And for the longest, nobody was even close. Okay. They always say fusion is always 10, 30 years away, forever. So there was for a long time this big gap of maybe taking out 10% of energy and you're putting 90, so not even close to breaking even. Okay. 2 years ago, we were in the news. For the first time ever, we were able to get more energy out than the energy put in. And there was a lot of news articles and really international rigor to make sure that this is not just a blunder. This is actually true, and we actually figured it out. So it took a while, but we were actually able to replicate it. The first time it happened, there was a track record of us getting closer, but from 1 year to another, achieving ignition was something that really doubt. And we've actually done it again and again and again since. This is a graphic showing you back in 2022, almost 3 years now, what is the shot that actually broke ignition. The red circle is the energy that came out. The yellow circle is the energy that was put in from the lasers themselves. So since then, we've been able to replicate it multiple times, some of them with way more energy than we actually put in, as you can see. So we don't fully understand what exactly made this, but we have a pretty good idea what are some of these factors, right? We don't have these experiments happening every day. For the most part, they're about 6 to 8 a year. It really varies. When we actually said we definitely want to achieve ignition, we want to see if we can replicate the previous experiment, maybe even go bigger, all right? But we have a pretty good idea of what are some of the key factors to get us to get more energy out than the energy that we put in. So this is the facility I work in. I'm a nuclear engineer. I work with designing the instruments that go inside of this target chamber. If you can imagine, every time we have these experiments, we want to take pictures, we want to take temperatures, we want to take measurements, and there's no single instrument that we can just go to the store and buy and put into our facility. So every one of those simple instruments to measure the temperature, to measure the radiation, we have to design and build our own. So I lead a team of scientists and engineers that come up with the main tools and the main instruments that go inside of there, just like those three that are shown in there, that can provide us information after every experiment, what went well, what didn't go as planned, how did the capsule happen on a nanosecond by nanosecond, how did it implode? We can get more information so that the next time we try to do it, we actually get better at it. Okay. This is a picture of the scale of the facility of this blown out. There's 2 of our technicians working in one of the diagnostics, just to give you an idea of how big this facility is. And that's me working on diagnostics. Like I said, I'm working on the engineering side. A lot of these instruments go through an entire life cycle, like if we were designing any other product, right? We 3D print parts, we test, we make sure parts fit. This is, like I said, about 20 years old of a facility. So a lot of this is retrofitting what's out there, making sure that what you design can work with the existing infrastructure. And I get to work with a lot of people from different backgrounds. There's a picture that we took about last year from everyone in the team. And there's a lot of physicists, a lot of mechanicals, sure, a lot of chemists, and actually a lot of biologists as well. here's me as probably one of the few nuclear engineers. But we have people with different backgrounds, all contributing to different aspects of what makes this work, of what will make this work in the future, right? That's a little bit about what I do, what the mission is for the facility. I'm happy to go into more details and talk more about it. So I'll save that for the end. Let me run through a couple of tips that I would like to give everyone and share in case you're thinking about any of these already, right? As you go through these years of your educational journey, one of my first things that I understood is you have to develop a strategy for what your educational journey is going to look like. You can't just stick to coming in, taking classes and hoping everything's going to work out. You really should put an effort into where you want to take your education. What type of candidate you want to be in the future for getting your dream job, right? You're working on the type of projects that you want to work for. So think about your free summers. Like I said, maybe they offer classes and you can advance your degree. Maybe you can graduate quicker. Maybe you can take internships. So start thinking as a strategy as opposed to just here taking classes on homework and then eventually something will come out of it, right? What do you want your resume to look like in 2 years, 3 years? Maybe the class and the program you're taking will get you there. Maybe you can do extracurricular activities, get involved in some research that's happening on campus, right? What type of, if you've identified a company or a type of project that you want to work for, research what type of staff do they hire? What type of background? Do they hire people in your field or they actually go towards something else? Those are some really good questions to think about. Secondly, get involved. And I cannot emphasize this enough, right? Not just come to classes and leave campus. There's all these amazing organizations that provide support one way or another to get you to excel in your college degrees. There's study groups, there's all kinds of faculty projects and research opportunities to join in. I got to meet people from being on campus and intramural sports, developing study sessions with people in my classes. These are some of the organizations I got involved in. There's many more. I was primarily in the engineering side, so these are some of the most popular ones. Maybe you do have some here on campus as well. But any chance that you can to socialize with people that are going through the same path that you're going is going to be great. It's going to be positive. So I encourage you to get involved. Third is invest in yourself and in your self-growth. I like to think of your college years as you're getting ready for the Olympics. Just like athletes have 4 years between every Olympics to prepare themselves, you're doing the same thing. Once you graduate, you're out in the world trying to perform as a professional. So think yourself how you split up your time, how do you prepare yourself to be the best person that you can be once you graduate. Right? Lastly, go to grad school and ideally for free. I'd love to talk to you more about opportunities to go to grad school for free. I'm going to put here my contact info if you ever want to reach out. Especially if you're going into a STEM degree, there's all these opportunities to really go to grad school for free, take advantage of scholarships, co-op opportunities with different companies. I want to show this graph out here because it shows what is the tendency of reaching higher educational degrees in the US as a whole. So every time you go one step up in your degrees, you're actually joining a much smaller pool of professionals, right? Once you get your bachelor's degree, it's a big win and you're already way above a lot of the applicants in the pool for the US. But as you move closer to master's, professional degrees, or doctorates, you're joining that smaller and more advanced pool of candidates that are really becoming subject matter experts on your field. So think about that. I think in the interest of time, that's all I got, but I'm happy to ask any questions and entertain any.
First of all, give your hands. Are there any questions? I have one for sure, okay? The size of that, actual size of when it was on the crane, you cannot imagine what dimensions are. Something that it houses 100 lasers, what's the dimensions?
So the diameter is about 18 feet of the first layer. What's not shown here is how there's about 6 feet of reinforced concrete. So just the inner core is about 20 feet in diameter.
And
Plus everything that comes out.
And remember, the pebble was very small, right?
Very tiny. It's about half the size of a Tic Tac. Put the picture again. Yeah.
Anybody has a question? If you don't, I'll ask. Okay, what temperatures do we reach with
Oh.
laser?
So we reach about 10 times the temperature of the center of the sun. And that puts us at, they actually do quote the temperatures because we measure them.
Yeah.
But it's really hot. Now, it's only for a fraction of a second. It's very small. And the entire experiment happens under vacuum. So there's no heat transfer to the walls or to the instrument. Very little heat transfer. Sure.
How do you collect the energy from the reaction?
That's a good question. We're actually not trying to collect the energy. We're actually just trying to measure how much energy comes out. Remember, the entire purpose was to prove that we can get more energy out than we're putting in. Once we feel confident, they're going to build a facility that will take that energy and absorb it to actually provide, become a reactor. But right now, it's not. Right now, we're only measuring how much is coming out, and it's all wasted. It's not going into the.
So is the energy like heat? So like what's the form of energy?
So very little is heat. The energy that gets released comes in the way of the particles that come out. You can think of a nuclear reaction in terms of gamma rays, X-rays, neutrons. All of those, in that fraction of a second where that implosion happens, that's what actually comes out of the fusion reaction. All of that eventually can be transformed into heat. We can boil water and run a steam generator just like any other plant does, right? But at this point, we're only, and that's why it's important to measure how much energy is coming out, because if it's not heat, we need detectors to measure gamma rays or to measure a certain amount of X-rays.
So does the stuff that you build include detecting like those chemicals?
It's almost exclusively. Every time there's all these questions. How do you know you've done a good measurement of the energy out if there's all these things that you cannot see and hardly feel, right? So it's being able to understand the theory part of it, and then put detectors that specifically detect that range of energies in such a tight window of time.
Two quick ones. First one is like, what drives you primarily with this occupation? Like, what keeps you going? Kind of like that driving force that motivates you to keep on.
Money.
Well, that's of course, I mean, I love money too, but I guess like, from like a more moral standpoint and like what drives you apart from money. And then also where you see the future of renewable energy, for example, electrical, nuclear, in the coming few decades, and like what younger generations would do if they want to look into that field.
Sure. So I'll tell you what drives me, outside of money, of course. Like I said, I was actually working as a mechanical engineer for many cool companies, and I thought I was making good money and I had a good career ahead of me. But I was always very curious on nuclear energy. Why is it that we're not doing anything else? Why is it that the reactors we have been designed for like 50 years? And really, at least my engineering career, engineering education, barely touched on it. So I knew there was a lot of potential. I just didn't understand why are we not doing anything more with it. When I looked into that, I saw that there's actually people trying to do things different. Right around the time I graduated, 2014, 2015, Bill Gates was launching a new nuclear reactor startup. Oregon State had launched a new design for a nuclear reactor that was the size of a truck. So there was all this initiative, so there was all this potential. And out of all the grad schools that I applied to, there was only one that offered a nuclear program. Even here in the West Coast, there's not a lot of them that offer nuclear engineering, nuclear science as a major. So that Oregon State offered. All the other ones were careers in mechanical engineering. And I decided to go to grad school for nuclear, not because of the money, but because of the curiosity, the promise that I thought nuclear energy had in the future. That's what drove me. The second question, how do I see the future for renewable energies? I definitely think it's not a solution. It's not just nuclear or just solar. I definitely think it's gonna have to be a combination. Right? The right path is moving away from carbon fuels, and the right path is to find a way that works with every community. Every country works and have different resources, and they operate differently. So it's definitely going to be a mixture. Since the breakthrough, there's been all these initiatives from private companies to take what we have learned from doing these experiments and take it to the private sector. A lot of capital investments and a lot of startups have actually originated here in Silicon Valley because they think they can learn from what we've done and put a reactor together within 5-10 years from now. Like I said, right now, our mission is not to create a reactor and put energy back into the grid. It's just to prove that we can do the science. So a lot of private companies are taking the breakthrough we had and coming up with reactor designs that could actually power our homes within 5 to 10 years.
May I interject one
Sure.
quick thing? Well, see, years ago, when I was teaching here, my old boss from the company I worked for came here and said, "Muslim, what are you doing? Why don't you come back for me in New Jersey?" I said, "Why?" He said, "What are you making here?" But I told him, "So I triple your salary. Come and teach. Come work for me again." I said, "What do I do with the money?" He said, "You can do whatever you want." I said, "This is what I want." My point to you is that if you find a job that you like, whatever it is, then you're not working. You're going to be having a great time. Alex had a question.
Oh, well, go ahead, Jonathan, first.
What was the longest sustained action? What was the longest sustained fusion action?
So they're not long. They happen all within the picosecond range. And that's because, like I said, when we call them a shot, we take a shot, we burn the entire capsule. So we're not putting new capsules in, we put up a new one, we shoot it, it gets consumed within picoseconds. And the energy that we get out within that reaction, that's it. Right? So no more. We don't continuously feed it. So, within the picosecond range, that's how much it gets consumed.
What does your typical day look like, and how does that differ from the other folks around you?
Okay, now that's a good one. I try to be a little bit more proactive, or just try to step away from the normal. Fridays I almost exclusively use for emails and replying to people. That's the only time that I can really log myself into my office and reply and actually have some thoughts. But throughout the week, depending on the project, sometimes we're in the process where we're designing things. So it's me building things with engineers. A lot of them in a whiteboard, trying to get the theory down. A lot of the times we actually build a thing and we now got to go install it. So it's actually being in the facility and coordinating. All right, this goes here, make sure there's all this safety things to consider. This is a thing I designed for a year, please don't break it, right? So it really varies on where you are in the projects. It can be very, right now, our years, our academic years, our fiscal years run from September, and then it's, from September to August. So right now we're planning for what are the projects that are going to be next year, because we kind of estimate how much energy we're going to get from shots in the next coming months. We want to know what instruments we should be designing for next year already. So a lot of the meetings are meetings with the scientists to understand what is that going to look like, right? What new things we can come up with.
Follow-up question, and feel free to pass on this, but I am wondering, and I think it's important for people to hear, how the current administration's attitude toward science has been affecting your work, and how you're planning for the future.
They're coming after you.
It's not new that, like I said, we're not a private company. We entirely depend on the funding that we get from the government.
This
And-
question comes exactly the right time.
Yeah, there's been, Congress has been trying to pass this budget resolution for a while now, and I think last week they agreed on next September or something on that. So in a way, it doesn't prevent us from continuing the work that we do, but it definitely enables or not enables future work, right? So you can imagine, we have now a facility that, like I showed, is been putting out bigger amounts of energy and bigger amounts of energy. So we now got to design things to withstand that, right? We never planned to be this successful. So we got to design our hardware and devices to spend, and that's going to cost money. That's going to cost hiring the right people, training them, and that we don't get that funding from the government. That just gets put in the background, right? And it slows down our ability to move forward and drive the science forward.
In that regard, does the size of the pebble determined by the amount of energy that you can control, or is it other factors?
It's other factors. We know where the inefficiencies are in our system, and we try the best to address them. But the mixture of the pebble is more important to like the size of it, what exact doping coatings there are, as opposed to how big of a pebble we get. Right? I don't think I have a picture here, but our system is not designed to have even larger pebbles than what we're currently using. the lasers, this is kind of like a, if you can see this, the lasers come from the top and from the bottom, so really restrain on the size of the pebble. We can change the chemistry of it, we can change the intensity of our lasers, how efficient they are, the timing of it, but not particularly the size of it.
How high of pressure you reach?
So I know that one from the commercial that comes out. It's about 1,000 times the pressure in the center of the earth.
Okay.
By the time the pressure, it's interesting, by the time the pressure hits in time, by the time the pressure wave hits, everything's in vacuum, by the time pressure hits our instruments, it's too late. It's decades away from the physics that are happening. So we very rarely interested in the pressure.
That's of these like pebbles and like.
Ah.
Do you like, when it's like, let's say an experiment doesn't go well, or you wasted a pebble, how much is it like cost and expenses?
Sure.
How does it affect you?
We have a good idea of that, and I have a good idea of that because this is a government facility. That means that anyone can actually propose an experiment to be run at NEF. And universities, NASA, private companies come up with ideas. They say, hey, I want you to shoot a pebble of this material because I came up with a brand new alloy and I want to see what happens when you put it in this radiation environment. So we know it costs right around $1 million per pebble. For every shot. So, and sometimes things don't go right? But it is open to anyone to just like any national laboratory for submissions for experiments. And you want to see if you have the background, you go present and say, hey, I want to pitch this experiment. It will happen. It's a national laboratory.
Is it possible to get a private funding?
Yeah. We serve private companies that want to have their goals are to test things for their businesses as opposed to drive science forward. So we do for that. We do have clients, a lot of them, private contractors here in the Bay Area.
Peter has a question.
Sure.
So why is the timing so critical? Does that do the symmetry of hitting the pebble all the time?
So it's very similar to imagine trying to pop a balloon with your hands, right? And if you don't compress very evenly, the balloon is gonna start creating this blobs of air. Right? So you want all the lasers to hit at the right time so that the reaction can happen very spherical, very homogeneous. We're trying that, we're trying to compress the atoms, so we're not compress it from all sides at the same time, so they don't try to escape from one particular area. Right? And if you can imagine a 4-pi distribution, you want to squeeze evenly from all sides. And that's kind of what makes us very different from some of the other countries that are trying to do this. Our lasers, I kind of lied a little bit, but our lasers are not hitting the pebble directly. They're hitting the inside of this gold cylinder, and the pebble's right in the middle. When the lasers hit the walls at an angle, they produce X-rays entirely symmetrically. So the lasers hit them at the same time, and they produce X-rays at the same time. Then the X-rays can actually do all the compression with all this, from all these angles at the same time. So that's why it's key that the X-rays, all of them start at the same time, and not just have ones first and the others.
Imagine trying to squeeze a balloon. If it is uneven, it goes all over, right? But if you confine the balloon inside the chamber and push that chamber, it works.
Sure.
In terms of an engineering perspective, what do you suggest, like, if you get stuck trying to design something and you're like, man, I don't know what to do next, or this material isn't working out, this material isn't.
So one of the things that I found amazing, and maybe I'm old school, but being able to walk into someone's office and always say, hey, just share your problem with them, even if it's just in a casual way, that sharing of knowledge, for me, has worked amazing. Because maybe the people that are around me, maybe they don't know the details of my problem or the details of why I'm working on this, but they have other areas of expertise. They have other ideas, right? And we're all different. So even just casually walking up to my peers often and say, hey, what do you think about this? They might offer you a brand new perspective, right? They might not have the entire solution, but they can actually push you in a direction that maybe you didn't consider before, right? And when you're trying to design something that's unique, right? They don't sell these devices at Home Depot anywhere, right? You want to be able to have eyes on all the approaches possible. And you sharing that information with your colleagues helps a lot. Often than not, I try to share what my problems are for work, what I'm designing to my friends that are not engineers or scientists, and they come up with great ideas. To my parents that are so far away from technology, and they might actually come up with a good approach that I'm gonna understand. So that sharing that information is one of the best tips I could do. I'm sure.
When it comes to internships, what are companies looking for when they're hiring?
So I think what I've seen, not only at the laboratory, but most other companies, is that they want to see at least your core set of classes under your belt, right? The class that you take in your first year, first, second year. And then they want to see that you're interested in the companies and the mission that the companies are working for. I think almost everyone understands that you're starting your career, right? So you're not going to be an expert, but you're going to be something willing to be trained in their operations, in their designs, and so that eventually you become part of their staff. That's primarily what they're looking for. As an intern, you want to get the experience, sure, but they also want someone that will grow with them so that 2 years, 3 years past when you graduate, you're someone that already started hitting the ground running. So I think that's one of the best advice. Look up what do companies do, what is this position exactly going to do with that team, and that show that initiative.
So is it disadvantage to me if I tell them that I want to transfer to like SoCal or something, so they know that I'm not staying here with their company?
I don't think so. I think companies, we were just talking about that, they'll, if they're interested in you, they'll make an offer for you to move across states, across state lines, right? I think that is less of an issue. They know that you're going to pursue a degree and you're starting out. But they also know that if you do a good job, they might want to bring you back for a job wherever you are, right? So moving across state lines is really not.
They bring you from anywhere. Anything else? Go ahead.
Yeah, so you mentioned getting like a master's degree kind of separates you from like, well, obviously getting a bachelor's degree is also good as well.
Yes.
But when does it get to a point where it's like kind of like diminishing returns, like unless you're trying to become like a professor? Because I'm like thinking about going for like a PhD, but like I'm not sure if like that's what fits with like my career path. Or wondering what you're like.
So here's the thing, as a PhD, you're gonna be the top of the top in your knowledge base, right? And it's really up to you what you want to do with that. There's obviously a lot, because you're at the top of your expertise. Universities want the faculty to teach, but so there are private companies or national laboratories. Those people, people with PhDs know the subject so well that you can actually develop knowledge that doesn't exist now. So companies are in the pursuit of that, maybe for new business ventures. The laboratories have almost, I think, most of the population are PhDs, masters, performing research, right? But at the end of the day, when you said diminishing returns, I think you really have to take a look at yourself and investing in yourself, right? It's never going to be a diminishing return if you're investing in education for yourself, right? It's never going to, whatever career path you want to take, you're really growing yourself as technically in your knowledge, you're growing yourself as a person. So I never see it as you're going to get less out of it than you get, right?
I want to echo what Mr. Gjemso said. Don't set up your goals based on degrees. Set up on what you want to learn. That is where it would get you where you want to go. Degrees come and go, countries come and go, but if you're interested in a subject, you pursue it wherever it goes. And that would be my advice.
That's it. You got to pursue that curiosity. It's going to drive you forward. Sure.
So I have a question for Morgan.
Okay.
They're asking, what was the hardest problem in your career?
Let's stick to the technical aspects of it. Well, one of the biggest challenges was I was just explaining the difference between fusion and fission. Before I started this job, everything I knew was fission. Everything I knew was technology that had been around for since the 50s and 60s. So a big challenge is jumping in without having. I know it sounds very similar, very familiar. They're completely different branches of physics, completely different branches of science. So I completely studied, or what I thought to study, one of them, and then I start a job with a top research facility doing something else. So a lot of the work when I first started was understanding the science behind it, so I can actually get to a point where I can contribute technically in something, right? I didn't understand a single bit of fusion. I knew, Iron Man used it for his reactor, but I had very little background, right? So part of it I remember was getting myself familiar with it. A lot of my colleagues actually didn't have a fusion nuclear background themselves. They had to go through the same thing. It's a very limited field, so a big technical challenge for me was trying to do my job and at the same time learn, after hours, what's actually going on to have a better idea. And that was one of the biggest challenges, to just try to get myself familiar.
Any other question?
How are you guys able to like increase? Because I noticed over time, like the energy putting in and the energy going out was like gradually like improving.
Yes.
Like how did you reach like the 2.2 to 5.2 ratio?
So that's a very, very good observation. So if there's a knob, an imaginary knob that we can push for the amount of power that's delivered by the lasers, right? We don't put it at the highest, just like any equipment that you buy for your home. You just want to run it at the most powerful one, right? Every time we actually have a shot, NIF self-destructs. So we don't want to run the energy lasers to the max. It destructs because our optical lines, our capacitors, everything that provides that laser is not equipped to handle that much energy, right? So little by little, after we had the first discovery, we figure out, okay, there's these ways that we can improve on, update our equipment that's been too old, so we can bring that laser energy a little bit higher and higher. That's a lot of part of the work right now. Is that we know that maybe the size of a pebble is not particularly important, but the energy that we put in is particularly important. So we want to try to get more energy in the lasers in. And these are lasers that have been running on for like 15, 20 years, right? So we find a way to get a little bit more energy each time without things falling apart drastically, right?
I noticed that from 20, you started there, you went up and then suddenly dropped in 2023. Why that drop?
So, like I said, there's many factors in every shot. And out of like the 100 factors, we think we know the 20 or 30 that actually play a big role. So we're constantly moving things around. Now there's shots in between that are not shown here where we did not get more energy out than we put in, right? But we learned something from it. So I'm sorry.
I can take that.
So that's why
So
probably.
So it's not linear increase then, it just goes up and down, okay.
A lot of the times, our ability, I think we talked about somebody else, how expensive it is to create this pebble. Our ability to create this pebble varies, and because we're trying to change it every time, it's kind of like, okay, we made a perfect cake, can you make it every week the same, right? Or even better, so it's challenging. These pebbles, I didn't mention there are cryogenic temperatures. They're very close to zero. So because of that, they're so small, they have to be very precisely machined and manufactured. There's an entire process. If you don't make them completely spherical, those tiny little pebbles, you won't get that symmetry that we're chasing. So there's all these factors on it. And I know for a fact that particular one, we had issues creating a target, right?
I'm aware that right now, Mike told us that a lot of what your lab is doing right now centers around solely nuclear fusion?
Yes.
Fusion, right.
Yes, yeah.
Fusion. So when, not that it's kind of like too ambitious, but like, at what time does your team think that perhaps you guys would be able to take such a project and then turn this into like a generator of some sort, or like, is that a bit far off?
So that's actually what was part of the pitch to Congress from 20 years ago was give us enough funds to build a facility that we can prove that we can get more energy out. And once we prove that, give us more money to build a facility that can take that energy out and actually prove that a reactor is possible, right? So when that pitch was made to build this, we said we're going to get ignition within the first 5 years, 10 years. It actually took more like 18. So I think sometimes, but that's definitely the plan, to go back and now we're the only country in the world that have got more energy out or even close to getting more energy out than we put in. Nobody's in any other lab facility in the world, in the different means that they're trying to do it, nobody has gotten close to. So I think we're getting ourselves in a very exciting stage for very soon have something else to take over, another facility.
Scientific process. All right, cool, thanks.
Okay? And Mr. Now you've been great audience, fantastic speakers. It's time for your pizza.
Yes.
All right? Thank you so much.
No, thank you. I'm gonna put my-
If anyone wants some soda, something like that, you can start making a line over here.
I don't know. Same thing, but with magnetic. They don't, sorry, they don't use lasers, but with magnetic magnets, find that plasma.